Good afternoon. We are Team 13, and our project is the Gulfstream Turbine Stabilization System. My name is Mauricio Rodriguez. With me today I have Robert DeSantis and John Valdez. The issue that we'll be going over is that one of the reasons why current turbines aren't more common in today's world is because of the stabilization systems and the complications that come with it. Our motivation is because ocean current turbine power is one of the most effective ways of harnessing green energy. In fact, it's even more reliable, more predictable than other forms such as solar and wind energy because we're able to measure and time currents more accurately. Our goal was to create a system to stabilize the turbines in an ocean current. Not only would it be cost effective, but also provide minimal impact on the environment.
Some of the other turbines we looked at for our research is the Francis and Capline turbines. They're mostly used for river situations where there would be a steady flow and they compress the flow. The two turbines getting tidal currents similar to ours are the CGen tidal turbine and the Ocean Energy turbine. The CGen on the right here has two large rotors and can move up and down to get the most efficient current. And the Ocean Energy has these small flaps and spins vertically, unlike the other our turbine and the CGen one. The problem with this is that it's susceptible to getting debris and things caught in these actual fins. The problem that both of these turbines have is that they're made for tidal currents, and they have a maximum depth. For example, the CGen is only good to up to 38 meters, so we want to look into getting into a much deeper depth. The first system we looked at is the Buoy System. It would be on the surface and could harness wind energy as well as current energy. The problem with this is it's susceptible to the surface conditions such as wind and waves, and there's limited turbine mounting area on the actual structure. The thrust positioning system is a large turbine with small thrusters on the outside. This would allow it to stay directly into the current, harnessing the most energy. Problem is all these extra moving parts and you're using the energy that you're trying to harness. The third system is the tethering system, which we chose to use. It's easier to change depth up and down, and there's much more area. For example, we just chose 4 turbines. The problem is the structure is usually much larger and requires more anchors to be stable.
I'll be talking about the structural system. We did our research on submarines and torpedoes to spend most of the time underneath the water. We covered the inner rings, fin, skin, dome, skin with the fin, and engine propellers. Our inner rings, this is the way our inner ring looks. We have a total of 6 inner rings. They're separated 6 inches apart from each other with a 5-inch diameter and 1/4 thickness. Our fins, we have a total of 8 fins. They're 7-inch longs. They have 2 holes on one side and 2 inlets on the other one to connect easy to each other and able to be taken apart by piece. Our skins, we have a total of 16 skins. Each skin can be taken apart and have a separate compartment to fix anything in the component. We have 8 holes to secure the skin to the inner rings itself. Our support beam are 3/4 wide, 7-inch long, and 1/4 thick. They secure the inner rings once you take all the skins apart and everything, with holes on each end. This is our dome. We have 2 domes on each side. 2 domes, 5-inch diameter, and 24 holes to secure the skin to the inner ring. Our skin with fins. This is our main piece in the middle of the body. It has 4 little fins coming out that helps guide the other skins on top with a 1/4 inch thickness. This is our engine housing. 2 little inlets, about 0.60-inch diameters, and they connect to the fins, and on one side the propeller goes attached. There's 4 of them on each end of each of the fins. This is our final concept, everything how it looks. On the left side is how it look with everything attached, all the skin minus the propeller, and this is how it look on the inner skeleton when you're looking at X-ray right through the system. Next, we'll be talking about our simulation. A force analysis measure of the outside force of the structure is stress and strain analysis. Measure how the stress and strain. We use force 10, 20, 30, and 100-pound force. We solve for Ramesi stress and strain and displacement. Right here is our 30-pound force. If you can notice that the stress is mainly concerned in the inner skin with the fins attached to it. Everything else, that's where the main stress on all of them was most affected by. Our strain had the same complexity as the bond, and as well as all the other 10, 20, 30, as well as 100. That was its main effect, was where the fins meet the other skin. our displacement. If you notice that the most of the displacement occur is at the end where the engine mount housing, because it's far off from the rest of the body.
Okay, for our design, you can see that we originally went for a 3D printed design where we would have the skins and the fins. The problem is that our two quotes were for $7,500 and then also $1,500. We considered the $1,500 quote, but the lead time was 30 to 50 days. And if we had any problems with needing to change dimensions or broke apart, we figured that we would be out of luck. So we chose to do the PVC, which was much cheaper, and the parts are readily available. For testing, it's also convenient because we tested multiple lengths as well as diameter, and the maintenance is also similar to the 3D printing, just making sure that everything is completely watertight for all the seals, and in a long term, any buildup on the actual structure. For safety, we don't have many safety issues with the actual prototype, but when we get to a large scale, we'd have to worry about the propeller spinning, and also for boats navigating in the area, we would have to have buoys and well-marked structure so that everybody knows where it is. For the three anchors we're in between, there's the plow, the stockless, and the mushroom. The plow is best for sandy bottoms, the mushroom being the best for very soft bottoms where it can create a suction. We decided to go with the stockless anchor because it is able to handle both bottoms really well, and it is also very available because that is what large yachts and ships use, so it's also cheaper. For the design calculations, we started with the volume and to get the buoyancy of our structure, as well as that way we knew how much weight we needed to have to anchor it, as well as how much weight we could put inside of the structure as far as turbines and batteries and things like that. For bending, we calculated the stress and the deflection. We also had the internal pressure from the depths that we were at, and blade power and thrust was needed so that we knew if the blades were actually going to affect the structure and stability. For the prototype cost, here you can see an itemized list of all the PVC that we used, as well as the propellers, the weights, and any hardware that was used to actually put the structure in the water. For the soda bottle test, that was the first one. As you can see, this is our best soda bottle. We started with a 2, 3, and 4 turbine structure to see which was the best amount and which was the most stable. We used the same anchoring weight and internal weight for each one of these tests, just so that we could solely test each amount of turbine. We found that the 4 turbine was by far the most stable, so that was the one we decided to move forward with. From here, we created the prototype and started testing in the pool, as you can see. In the pool, it had a 0.5 meter per second flow from the jets, and from here we tested the different angles of flow that the water could hit it. Also, the minimum and maximum loads for the inside of the structure that we can have, as well as the placing the weights in different areas to see how that affected our structure, and the attachment points, which made the largest amount of variance in our test, because if the attachment points were not perfect, the structure would tilt from one side to the other. From here we moved to the ocean testing. We started the ocean testing at a higher current of 1 meter per second, as well as winds and waves on the surface, which could also affect the stability. We went with the same weights from pool testing that worked the best, which was 10 to 16 pounds in the actual internal part, and then a 4-pound weight in the bottom of the turbine housing to keep that one at the bottom. From here, we tested to see how we also used real anchors to see if that affected, and the attachment points were the same as in the pool testing. Here we have a couple of videos next of the actual structure in the water. As you can see, the upper blades are spinning faster than the bottom blades. This is because the highest amount of current is at the top 1/3 of the depth of the water. So that, here it's a little bit shallow. So for optimum, we would want to stay at the very top, but still under the surface.
Here we have a table looking at the division of responsibilities among all the members. All the members have their own major and minor roles, and as they contribute, everyone contributes to the project. Here's a timeline showing a rough estimate of the timeline in which it took in order to create our project, As you can see, we started in September with our initial research and designs, and we worked our way to the final design in April while working on the report throughout the entire time. These are some of the standards that we used in our project in order to incorporate looking at turbines or the material used or of course the units used for measurement and some of the environmental standards. Looking at the environmental aspect, we looked into studies that were conducted over long term of current turbines that are already in place in the world, and there are 4 factors that we considered was sounds, wildlife interactions, current energy depletion, and pollution. All these studies showed minimal long-term impact on all these factors. However, further studies still required in order to ensure more conclusive results. Here's a cost analysis on a full-size structure of our prototype if it was about 20 sizes longer, a lot larger, and using fiberglass as the material. Here we have, looking at our global aspects of our design, we believe that we can use our design and make modifications in order to be used for other areas that are close to turbines that perhaps could, we would incorporate their different speeds or different depths, different temperatures, and the tidal change that occurs because of those temperatures. We'd use the results from our studies in order to incorporate it into the information we gather from these other currents. Looking at our design compared to what companies that are on a global scale, majority of the ocean technology that's in place is still relatively new, with companies making use of technologies that are already enacted for turbines and marine systems. And most of the earlier work comes into determining the device endurance and performance, such as we've done with our project. The lifelong lessons that we've learned throughout this project is one, teamwork, having to work with people with different skills, different time schedules, having to communicate with everyone to meet up or make sure everyone was on their part. We also experienced conducting research in the background for our structure, the development, design, and construction of the prototype, and the experimentation that is needed in order to find the results for our project. We also feel that our design will serve as a foundation for any future projects that perhaps students even in FIU may conduct on current turbines. So in conclusion, we were able to successfully construct a prototype that was able to stabilize in the current while also making it relatively cost effective. We believe it will have minimal impact on the environment, and we believe this design can be incorporated around the world. Any future work that would be looked into this would be further studies on the long-term environmental impact that our design would have. We'd also like to incorporate perhaps some other design modifications such as dual blades, retractable anchors, or even a ballast system. And we'd, of course, our project being a foundation, incorporate any future advancements in the technology in this field. And we look towards the development of a full-scale structure for either commercial or personal use. That concludes our project. Are there any questions?
So what's the measure of how stable or how much you achieve the stabilization compared to other existing technologies?
So we placed the weights in there to get kind of an idea of what was the, for internal parts that we would need. So we tested minimum weights. Obviously with no weight, the structure was not very stable and it was easily spun from currents hitting at an angle. And then we also went to the other extreme and tested up to 24 pounds inside the structure and another 4 in the bottom. And at that point it sunk. So we realized that was too much. But we found that we put 5 pounds and 5 pounds in each side, and then 4 in the bottom was one of our best test weights, up to 8 pounds in the top structure.
Yeah, it'd be nice if you have a graph of your test results that that will show people how you optimize your design to achieve maximum stabilization.
And along those lines, what were your design alternatives or iterations? Were there any other design
Yes,
alternatives you considered?
So you see here, like this is a separate part here. So we can take these off, and we tried a different length, but the shorter was very susceptible to sway. Because we had found that online from our research of submarines that a 6 to 7 to 1 diameter to length ratio was supposed to be the most efficient. But that's the original one we tried, and it was very susceptible to sway, maybe because submarines are more underpowered to where this was just anchored. So we found that a 10 to 12 to 1 ratio worked much better without being excessively long.
It faces the top side of the submarine. To come out of the submarine, it's located in the middle of the sub. And it's not looking in the front or anything. So we used our propeller. We put our arms right in the middle of the centerpiece of the whole thing.
Just a quick question. So the propellers, I'm still a little confused. Are you trying to stabilize using the propellers, or do the propellers stabilize?
We're trying to get the propellers don't actually create that much force compared to the overall size of the structure. So we did do the calculations for the propellers, but we initially just wanted the structure to stay stable, because there's 3 degrees of freedom to where it can go, the front can go down or up, side to side, and then also rotating. So our main goal was to not have any of those problems.
Most of the Gulf turbine engines are attached to the seafloor valve, which they're damaging the seafloor. What we came up is trying to come up with a system not to damage the seafloor, where it's in the middle of the ocean, and the only thing that's touching the ground is the anchor. It's easy to, and it can go up and down using a ballast system, going up and down to whatever depth you want, and easy to take it apart, take it out of the water for any kind of maintenance, or any kind of repair. The ones that are in place now are all attached to the bottom of the ocean.
So you put a turbine, sorry.
No, go ahead, go.
You put, the ideal design would be put the turbine inside the center channel, right?
But we would
Inside
have,
of it.
we would have generators in each housing to a central converter.
Okay. And this structure will hopefully keep it from spinning in order.
That's what I don't see.
Yeah.
Well, in this case, for example, if you have a higher current on the left 2 motors,
Mhm.
right?
Well, it's a little hard to see, like it would actually sit like this because there's more weight.
Okay, let's say the
Yeah,
left
so,
motor.
because like this we originally thought, and then we had a lot of things. So we've had a defined bottom with the weight, and then also with the weight would be at the bottom of the center structure, which helped.
Well, even if it's more current, since we don't have anything implemented in structure inside, it will be all commercial loop up. So if there's more current on one of the turbines, the other turbine could adjust for it and slow the pace down. Our main concern was just doing a structure that was easy to be able to put turbine engines without flipping around. When we tried our 3 system, the turbine, the Coke bottle kept swaying over, and when we tried 2, it wasn't working properly. But when we put in the 4th one with actual weight, actual thing, it was able to stay in the water. We used the current of the pool, push it in as our source of propeller. It stayed perfectly fine without adjusting it and making it. Every time we put in like a 3 bottom and everything, it was moving all over the place, and it wasn't. The 4th one was able to adjust it perfectly.
And that tells me that it's not enough, just only by the structure, it's not enough to stabilize it. You need other things to do, like for example, like you said, maybe do something to the motors. But if your idea, if the concept was to make a stabilization system, right, then it would have been good to at least approach that, right? You can build a structure, that's okay, but then what's the next step to make it stable? And I can see the vertical more like a pitch because of the fact that you have center of mass, but I can't see stabilization this way. So again, with another algorithm or some type of
You mean for rotation?
for rotation horizontally, I don't see how you can prevent that unless you have another type of
Well, we
approach.
would have 2 anchors off the bow.
Oh, you do have 2 anchors?
Yeah,
yeah,
two
it's
anchors.
In the back
If you
end,
look
in
at
the
our
front?
structure, we
Oh,
have
okay.
1 hook here
Okay.
and then 2 here on the
Gotcha.
sides, which would serve as.
We didn't put
So
bring the
that-
anchors.
Oh, I see. Oh, so that's a stable, this
Right.
thing
Yeah,
is always
it's a
there.
triangle.
And it's just getting, okay.
It's not gonna move from where it is.
Gotcha.
And if you look at the video, when you play the video back, the current in it, and there's anchors at the bottom, which kept it in the pool. You You see it in the pool in the picture, there's anchors holding it down. So it does have anchors, but it's not anchors that are bolted to the sea floor.
Sorry, I thought I saw them only at one end, that's all.
No.
Okay. And you guys didn't generate any electricity or anything? with
No,
this?
We did
That
some
was-
calculations for the actual power that the blades would produce, mostly to get the torque from the blades and the thrust, just to see. But we don't actually have a generator inside.
But the main purpose of the blades is for stabilization.
No, the blades are what create the power. But we just put them on there to see, we wanted to make sure that, if we made the structure and it was all worked good, and then we put the blades on and it started spinning, but that didn't happen. But we just wanted to make sure that wasn't good.
We wanted to make sure that we could have turbines on our system and that they would be stabilized in the water.
Yeah, it's more like the harnessing the energy from the ocean. Yeah.
So this is not meant, okay, I had it completely different anyway. No wonder I thought you would play anyway. Sorry.
No, we calculated the weight of all we calculated the weight of everything and went not.
Yeah.
You thought that the turbines would help stabilize it?
Yeah, I
No,
thought.
we're
that you were-
stabilizing
yeah,
the turbines.
Gotcha.
We got everything but the turbine.
That one is my commercial.
No wonder.
And my question is, mostly I think you kind of answered is, once you get it in there and then you got the waves causing the blades to spin, and it all goes, you said towards the center tube, all the energy you're creating, how are you getting that energy to the outside world? That's where I'm confused.
Yes, we would have to have a very long cable would be the thing. Or we could have actual batteries inside the structure, depending on the weight of it. And a larger scale would allow for much more weight to be put inside.
Okay, because I'm trying to see how you would use that to connect to the grid.
Well, that was one thing that's nice about the Gulf Stream here